Thank you so much. I come from about 200 feet above sea level. So, very excited to talk to you about open source AI infrastructure. I've been working on AI research for about a decade, and tech stack AI has changed a ton over that period of time. And as a consequence, the software stack for running AI has also evolved a tremendous amount. And I'm going to talk more about that software stack that we see a lot of companies standardizing on for managing and running their compute-intensive AI workloads. And to motivate that, I'm going to start with some of the main changes that we see in AI workloads and how that's evolving. And so I'll start with just 2 slides on my background. So I did a PhD in machine learning at UC Berkeley starting in 2013. And I was focused initially on machine learning research, so reinforcement learning algorithms, deep learning training algorithms, and not at all on distributed systems. But about halfway through the PhD program, realized that I was spending all of my time not on the algorithms, but on managing clusters and trying to scale the implementations of these algorithms to get them to run across a bunch of spot instances in the cloud or across a bunch of GPUs. And AI is very computationally intensive, and so this seemed like a huge bottleneck for us. And my co-founders and I, we started, Philip and Jan in this picture, we started Ray. So it's an open source project for scaling Python, so scaling compute-intensive AI workloads. And at the time, we were building it for ourselves, for other researchers, for early adopters who really cared about scaling AI workloads. But this was 2016. We started the company in 2019 after graduating. But the real inflection point for Ray was with generative AI and ChatGPT. And so since then, Ray has taken off. It's been adopted widely across the tech industry. Companies like Uber and Pinterest training all their models with Ray, or it's being used by companies like DeepSeek and Tencent and ByteDance and Runway and many different companies. And so the real inflection point here was generative AI, just because everyone started caring about AI and the need for scale, bigger models, more data, more GPUs. The need for scale just became a lot more obvious. And so a lot of things have changed since then. Now, I mentioned AI has been evolving, and I want to talk about 3 specific ways I think AI is evolving. And when I think about AI workloads, I'm thinking about there's a lot of AI workloads are powered by 3 main types of use cases. So one is model training, one is model serving, deploying the model, and one is data processing for preparing the data and getting insights out of data. And I think all of these 3 workloads are really evolving. I'm actually only going to go deep on one of them, but there's a lot to say about all of them. So with data processing, people have been processing data for a long time. The big change here is the rise of multimodal data, which I'll say more about in a second. With model serving, people have been deploying models for many years and powering their products and applications. What's new here is the rise of agents and multi-agent systems. And so model serving is becoming far more complex, along not only multi-agent systems, but a huge variety of different types of models, from reasoning models that are very expensive to cheap embedding models and other application logic. And with training, a lot of people have been training models, pre-training large models. But what we've seen recently is the rise of post-training and reinforcement learning as a way of really pushing the frontier of AI capabilities. And post-training workloads are far, far more complex than pre-training and regular training. And as a consequence, post-training has evolved its own tech stack. So I'm going to go talk a little bit more about multimodal data processing. I sometimes call this multimodal data processing, sometimes AI data processing, sometimes GPU data processing. But I mean the same thing by all of them. What's changing here is really the rise of multimodal data. So images, video, audio, text, sensor data, and all different types of data. And this type of data has existed for a long time. But historically, we haven't been able to get as much value out of it. Businesses have not gotten as much value out of it. And part of the reason for that is that we didn't have a good way to work with it. And what's changed recently is the emergence of powerful multimodal models that can actually take a video and watch it and summarize it, or read a PDF and analyze it, or look at a bunch of robotic sensor data and predict the next action to take. This is all relatively new. Not only multimodal models like that, but embedding models that work with all different types of data. And so, of course, historically, the dominant form of data that organizations would work with to analyze and get insights was tabular data. And the way you would process this tabular data might be with SQL queries or other types of simple analytics. But the way you work with multimodal data is, in a lot of cases, you run inference on that data. And if you're running inference on that data, then you're often doing that on GPUs. And so what we've seen is a lot of data processing shifting from essentially this paradigm where you run SQL on CPUs to being about inference on GPUs. And this is not to say SQL is going anywhere or CPUs are going anywhere. What's happening is the addition of multimodal data, the addition of inference and GPU-heavy data processing into regular data processing pipelines. And that's a pretty fundamental shift. And if you think about existing big data processing systems like Spark, Hadoop, Flink, which are battle-tested, mature systems, when they were designed, they weren't designed for GPUs. And so as we have more multimodal data, as data processing shifts to GPUs, there's a need for a new tech stack to support that. OK, so now let's talk about, this is about how AI use cases have been changing. I want to talk about how that change has led to a new tech stack. All right, so here are the different use cases at the top. I'm bundling all these together as different types of AI workloads. You've got training workloads, data processing workloads, agentic workloads. And under the hood, or at the very bottom, this is all powered by GPUs and other hardware accelerators, and CPUs, of course, but really GPUs. And so the way I've drawn this diagram, as these workloads at the top are becoming far more complex, there's a growing need for this software stack in between that connects the applications to the hardware, basically. And that's a quite complex software stack. And many companies have written publicly about their tech stacks. Working on Ray, we've had the opportunity to work with hundreds of companies and their platform teams and infrastructure teams and AI teams to see how they build these types of software stacks and manage this internally. And just to share one diagram, no need to read the details. This is to show you that there are a lot of moving parts. This is from a blog post that Roblox wrote, illustrating how they run these workloads. And the point here is that there are many moving parts. Okay, it's a lot of complexity. It's not just one framework. Okay, but one of the interesting things is that all of the different components tend to be open source. And I'll say more about that in a little bit. Okay, so instead of having this type of diagram with tons of boxes and arrows, I'm going to try to divide it into a few different layers where each layer has a different set of responsibilities. So the first layer should be pretty familiar. This is what I'm calling the training and inference framework. And I'm leaving a little space because there are more pieces. But the centerpiece of this is PyTorch. There used to be tons of different deep learning frameworks. When I started at Berkeley, there's one from Berkeley called Caffe. It was very popular. People were using Theano, Torch. There was MXNet from CMU and Amazon. There's TensorFlow and many others. But today, it's really PyTorch. And JAX is popular as well, especially for running on TPUs. Now, the responsibility of this layer is about running the model on the GPU. That could be running it for training, running it for inference, but running the model really fast on the GPUs. Okay, there's a lot of depth there. And you could, if you wanted to, you could take this layer and expand it into many other layers itself. But one part of this layer that I'll highlight is an emergence of, as models have gotten larger, there's an emergence of, the important model parallelism and parallelism generally have become more important. You need to shard the model across a bunch of GPUs. And there are a number of specialized frameworks for doing this. Some are more focused on training, some on inference. Some are focused on general models, all different types of models. And some are focused on transformers. So transformers are the architecture behind large language models. And two that I'll highlight here, well, vLLM and SGLang are super popular open source inference engines for transformers. Transformers are important enough that they deserve their own category of optimizations and frameworks. And just to give you a sense, there's a ton of depth just in those boxes alone. FSDP and DeepSpeed are more training focused. They work for any type of model. Megatron is training focused as well, and it's, but also for transformers. So again, the responsibility of this layer is about running the models on the GPU really fast. Okay, so the next layer is where I've been working, and I'm calling this the distributed compute engine. So the responsibility of this layer is about distributed computing, about scale, about managing processes across a cluster, about managing the creation of those processes, the life cycles of those processes, the communication, sending messages, RPCs, data between those processes, right? Data ingest, data movement, failure handling, resource management. If you're running a big workload on a bunch of spot instances, some of them get preempted. How do you reconfigure the compute, the workload on the remaining hardware to continue operating smoothly? Or how do you, request more compute and auto-scale of the workload because you need to scale up? So that's what I'm calling the distributed compute engine. The core responsibility at this layer is about solving the distributed computing challenges when you scale. And the third layer I'm calling the container orchestrator. So Kubernetes should be very familiar to many of you. Kubernetes has really emerged as the standard at this layer. And if you may or may not know about Slurm. Slurm is also super popular for orchestrating workloads. It's more popular among researchers. I'd say Kubernetes started its life cycle focused on microservices, and as a consequence, does biases a little bit toward online workloads. Of course, supports all of the workloads. Whereas Slurm biases or is more popular among batch workloads, so think training or data processing and stuff like that. And of course, there are many different ways of doing this, but Kubernetes has really emerged as a standard. And the responsibility of this layer, I would call it compute orchestration. It's about managing container creation and container lifecycle, interfacing, provisioning the compute. If you're running on the cloud, talking to the cloud provider to acquire more compute or return compute that's not being used. It's about multi-tenancy, supporting many different users and many different jobs running on the same shared pool of compute. And just to illustrate how some of the responsibilities get divided between these layers, if you think about something like resource management or auto-scaling, if I'm running a big data processing job and I want to, I want to scale up, okay? So if you look at that responsibility gets split across the distributed compute layer and the container orchestration layer. Right, so the distributed compute layer is actually, so Ray, for example, is aware of the workload. It knows that if there's more compute available, this workload could take advantage of it and redivide itself among, across more compute resources to speed things up. And so it needs to request more resources and talk to Kubernetes and talk to the container orchestrator and say, hey, this workload would benefit from more compute resources. And then Kubernetes is responsible for actually providing those resources. Okay, so similarly with scheduling, Kubernetes will say, hey, there's this user trying to run this job and this user trying to run this job, and I'm gonna schedule this, run this job now. So kind of scheduling at the level of jobs. And then Ray, within that job, will say, okay, this particular function gets run over here, this particular function gets run over here, we're gonna send this message from here to here. All of the sort of fine-grained scheduling within the job happens at that layer. Okay, so there are subtle interfaces between these different layers. One of my favorite things about this, though, is you'll notice they're all open source. Everything here is open source. And as software stacks as the technology matures, the software stack sort of standardizes over time, the community tends to standardize on open source software. That's something I've noticed, at least for the period of time I've been working in AI. All right, so I just want to say there are real benefits to using this kind of tech stack. companies I'm not talking about here, but I've worked with Pinterest and Uber and Roblox. And all of these different components appear, play an important role in their tech stack. We've worked with companies like Instacart, where by adopting these technologies, they are now training on 100 times more data. Amazon wrote a blog post about migrating to some of these technologies, and as a consequence, saving over $100 million a year. So there's really profound impacts here. The last thing I want to say is that if you're interested in open source AI infrastructure, we run our Ray Summit every year in person in San Francisco. It's happening this November. We go deep on AI infrastructure and really this whole tech stack. And I'd encourage you to check it out. Thank you so much. Thank you.